So Danny and Panpan deserve all the credit for organizing the workshop, but I did offer to help out tonight because it's exceedingly early in Germany right now. And so it's my pleasure to moderate this third panel. I'm lucky because the 4 speakers we have basically need no introduction, so my job is extremely simple. But let me just tell you quickly the rules that we've been trying to follow this to organize these sessions. Danny, if you want to show the next slide. Oh, okay, well, I'll introduce everybody as they come up. So we have the talks organized in 2 groups. The first 2 speakers will have 10 minutes each, roughly. And then we've allowed some time in the middle to have the panelists, ideally, talk amongst themselves and grill each other with hard questions and insightful comments. And then David and Leslie will go in the second half. If there's time, we'll do that again. But I guess in the first sessions, we've gone pretty much straight into the open discussion just to stay on schedule. And the open discussion, we will turn off the microphones or the Zoom recording so that everybody can unmic and ask questions and not worry at all about being recorded. And that's your chance to ask your hard questions. Okay, I think our first speaker is Chelsea. Chelsea, if you want to share your screen. So like I said, all 4 of these presenters need basically no introduction. So I'll say something less interesting, I guess, but I got to know Chelsea when she was an undergrad at MIT before she went off to Berkeley. And it's been an absolute joy to watch her like just explode into the robotics scene and quickly become one of the clearly most visible people in the field of learning and robotics. It's always a joy to hear her thoughts on this and have her push us in new ways of thinking about things. So thanks for coming, Chelsea. Let us know what you're thinking about.
Great. So in the theme of the workshop, I'm going to talk about bridging learning and planning for flexible, generalizable robotic manipulation. And I figured I would start off by actually giving my definition of learning and planning, because it might differ from other people in the workshop. First, I guess, rather simply, I view learning as using data to form components of some system, for example, a robotic system. And I view planning as, given some task specification, forming a course of action that satisfies that task specification using a model. And what I think is really beautiful about both of these tools is, first, for learning, it has the potential to allow systems to generalize in open world settings. And we've seen repeated success stories of this in computer vision and robotics. And for planning, I think that it gives us the flexibility to solve tasks that we didn't kind of necessarily anticipate during training. We don't need to know all of the tasks that we're given, and we can simply be given a task specification at test time and solve that task on the fly using some model that we had ahead of time. And so I think that both of these tools are quite useful for robots. And in particular, I think it's quite nice when we can realize the promise of both tools. And to do this, I think that kind of the general recipe that we could imagine doing is to use planning and plan over learned skills using learned models. And in particular, what this might look like is we use broad data sets, since they will facilitate broad generalization, use this to learn models and skills that generalize well, and then plan over these models and skills in order to flexibly solve tasks, even if we weren't given those tasks during training. And so in this very short talk, I'll give 2 examples of how we could actually realize this recipe in concrete ways and try to get the promise of both learning and planning. So the first example will be to plan using learned visual dynamics models. And what this looks like is we first collect some data. We use this to learn a predictive model of the future given the actions that the robot takes. And then given this model, we can plan using this model to try to solve tasks that a user gives us at test time. And there's a number of different ways that you can instantiate this more concretely, but to collect data, you could, if the skills that you want to solve are relatively simple, you can script data or collect data fairly randomly. and even potentially run the robot overnight and collect lots of data with lots of different objects. The predictive model could be a video prediction model, it could be a latent space model, and if it's self-supervised, then you don't need labels for all the data that you collected. And then you can do planning with using a variety of different tools. What I'll show today is the sampling-based optimization, but you can use others as well. Okay, so this is the general recipe. Collect data, learn a predictive model, and then plan using that model. And what I think is quite nice about this particular instantiation is that you can use a single model that you've learned for many different low-level skills. So for example, if we collect a lot of random data as well as some demonstration data, we can allow the robot to solve tasks that weren't in the demonstration data, like using a broom to sweep items into a dustpan, to reach objects like this blue object that are out of reach when the robot is constrained to move within this green region, and also to use objects that the robot has never seen before as tools to wipe objects off of a plate. So this is one example, and if you more recently we've looked at training these models on kind of cross-institutional data across multiple platforms, and then fine-tuning it on a small amount of data from a new environment. And this also allows you to solve tasks that were specified in this case with goal images. And so, for example, you can give the robot a goal image of trying to sweep this object into a dustpan, and the robot can use planning and its visual dynamics model to successfully solve the task. And likewise, you can also give a goal image of trying to kind of wipe this object off of the plate, and the robot can figure out that it should go down and grasp the object and use it to push the object off of the plate. Okay, and if you give these models good data and you develop models that are kind of sufficiently expressive enough to learn these kinds of dynamics models, then you can actually get a pretty high success rate with these kinds of methods compared to models that aren't expressive enough to represent this data. So this is kind of one recipe in which we could combine learning and planning. And really the takeaway, for me at least, is that we can accomplish vision-based manipulation of objects that the robot has never seen before, and use planning to allow the robot to solve a variety of tasks that weren't specified during training. However, one thing that you might notice is all of these skills are relatively simple, kind of short horizon skills. So what I'd like to briefly talk about in the second half is how we might look at longer horizon tasks. And in particular, what we're going to do is follow a fairly generic recipe that's been done before in a variety of different works, where we first learn some skills, then specify some model over those skills, and then plan using that model. Of course, I don't have time to go over all of the literature that follows a recipe like this, but one thing that we're going to experiment with in particular is trying to use a reinforcement learning method that can learn robust vision-based skills that are essentially robust enough to be able to be sequenced to solve long horizon tasks. And so in particular, the way that this is going to work is we're going to try to learn a set of 14 different image-based manipulation skills. And we're going to do this by first training a autoencoder and a latent dynamics model in that latent space. And then train this model so that it can effectively reconstruct future images. This kind of latent dynamics model can be trained on data that was collected across all 14 skills. And then for each of the skills, we are going to specify some examples that show the goal of that skill. For example, inserting the marker into this marker holder, and train a classifier to discriminate between positives and negatives that the robot collected. And this classifier will serve as the reward function for learning a Q function with reinforcement learning. This Q function and the reward function will be trained per skill, and the Q function can be combined with the model in order to execute the skill at test time. Okay, so this is the skill learning approach. And it allows us to learn skills directly from raw RGB images. And then once we have these skills, we're going to specify the pre and post conditions of each skill using image classifiers. And we can actually reuse the image classifier that was used as the reward function for the post conditions, and we can train some additional image classifiers to help with specifying the preconditions. And then we'll use an off-the-shelf symbolic planner in order to actually sequence these skills to solve a particular goal. Okay, so we're learning the skills, specifying the pre and post conditions, and then using a symbolic planner. And we tested this on 3 different long horizon tasks. In the first task, the goal is to place these 3 objects that were on the desk that the robot didn't see during training into the cabinet. And sorry for the choppy video, but this involves essentially opening the cabinet, picking up the objects and placing them into the cabinet, and then eventually also closing the cabinet door. Okay, and then in the second task, the goal is to pick up each of the markers and place them into the marker holder. And in this case, the skill of reorienting the marker and the gripper was scripted, but all of the other skills were learned. And then lastly, this last task is to essentially rearrange all of the objects into different positions. And this required 12 unique skills to be executed in sequence. And all the objects were kind of not seen during training. And overall, the kind of success rate of all of these tasks was about 17 out of 20, or 85%. So again, kind of the takeaway here is that by combining learning and planning, we can get vision-based manipulations of novel objects and the ability to not just solve one individual task, but a variety of different tasks. And kind of the general recipe of actually doing this is to use planning and performing planning over learned skills using learned models. And given the nature of this workshop, I figured I would also comment on what I think is missing. And I think, to me at least, the #1 thing that's really missing is really fully on the learning side, which is trying to actually allow robots to generalize broadly to new environments, to new tasks, to new objects. And we're starting to see some of this, but I think that it's not nearly to the degree that we've seen in other domains of machine learning. And I think that really a big missing ingredient here is to try to reuse broad offline data sets. We see this done all the time in other domains of machine learning, whereas in contrast in robot learning, we're always kind of recollecting data for new experiments and new projects. And I hope that if we can reuse broad offline data sets, we might be able to allow robots to generalize in open world settings. I'd like to thank my students, especially Bohg and Annie, who led the projects that I presented today.
That was awesome. Thank you very much. So we're going to move right on to Dieter. So please have your questions ready, but hold them for just a few minutes. Dieter also needs no introduction, but let me just say that, let's see, my fondest memories with Dieter have been like at robotics conferences over the years. Back when he was a perception guy more than a you know, planning and control guy. But he would always listen to the talks and be very thoughtful. And then he'd say afterwards, like in the hallway, he'd say, you know, Russ, that was really good, but don't you think it'd be way easier with learning, right? Dieter, you remember the number of times you said that to me? Like, you're making manipulation look really hard. You know, shouldn't you be using learning for that? And it's been fun to watch his ideas change and evolve, and certainly I think he was right in a lot of ways. So, but you've certainly been thinking about it for a long time. So please tell us what you're thinking about today.
Hey, Russ, thanks a lot for inviting me. Of course, the great introduction. I'm still a perception guy, and of course, it's all about representations, as I'm sure many other people have already said before. I want to focus on one specific aspect of this whole puzzle, especially related to manipulation. And I want to give 2 examples from some very recent work that we haven't even been published yet. Just for context, of course, we all know task and motion planning is kind of extremely powerful, extremely capable when we have a system that can reason about high-level actions and also a kind of the low-level control and can do planning in this space. These systems are super powerful, and especially, of course, in simulation, they work extremely well. And one question is, how can we get them to work in the real world? But again, I think even in simulation, it's not easy to solve these tasks, and there are very capable and powerful tools out there. for these kind of tasks nowadays. And one big question, of course, is if you want to execute these in the real world, how do you, for example, estimate the state of the system? You need to know exactly the 60 pose of objects. You need to know models and things like that. And these assumptions are in the real world just often you just can't make those true. So in some first line of work, what we looked at is, for example, can we get away without explicit object pose estimation? And we had a project where the input to a network is, for example, a camera image, and the system was trained to just predict, for example, the logical state of a task in motion planner or an execution behavior tree, for example, where the system would be trained to predict things like, is the drawer open, is the sugar box on the counter, and things like that. And we could even train it from simulated supervised training data then to generate conditioned on what the next step in a plan should be. They would also then, for example, suggest motion for the manipulator. The problem with that system was, however, that it was really just trained from image directly to logical states or to controls. And there was, I think, just a lack of structure, which means it didn't generalize at all, which means if you train it on the counter on the sugar box and there's another object, it wouldn't be able to make any statement about that. So it was really kind of a propositional logic state, which means there was no generalization at all. And I feel like it was really lacking structure. So now if we move on and see what, for example, especially the vision and the NLP community has developed, then I think we have to admit that they came up with some really powerful techniques over the last years that learn embeddings of visual and language data. I'm sure many of you have seen that. Some examples are like the language models, BERT, GPT-3, but also visual embedding learning, techniques like MOCO, SimCLR, and many of these techniques are actually trained with a really simple way of supervising them, right? You just kind of show them images and say, these two images should be embedded very nearby because we think it's kind of the same thing. And to generate these pairs of, let's say, same versus not same, what they typically do is they make like flips to images, or they generate certain crops of images. And I must say, whenever I see these results, I'm really blown away, and I'm very impressed by what these systems are capable of. So from a robotics perspective, we then tend to say, oh well, but they're still too simple, and robotics is so much harder, and they're not good enough for 3D spatial reasoning, so we can't really use them in robotics, and we don't have that kind of data that the people have in NLP in computer vision. And another example I really want to highlight is also the clip model learning, for example, that really just learns from extremely weak supervision. If you haven't seen this line of work, I really encourage you to take a look at the papers out there. But at the same time, when you really look at these results, it is shocking from how little supervision they can learn so much, and the capabilities really transfer to many different recognition tasks. And I don't think we have anything in robotics that has learned representations that have that kind of generalization capabilities. So the two examples I want to give are kind of inspired by some of this recent work. And the first one is learning object-centric representations, where the idea is the input is an image, and we also have query objects. So these are objects, for example, for which we have a single image of the object, and we can now feed that into a transformer network and outcome embeddings for these objects. So in this case, we queried these 4 objects, which gives us 4 embedding vectors, and the embedding vectors are trained in a task, in a manipulation system, in order to predict these predicates that a task planner, for example, would use. Is the blue block stacked on the green block, or is the robot in a good position to pick up the object? And we train it just with this logical supervision. And what's nice about the representation, it's not fixed to the number of objects. You can query also 5, 6, 7 objects, and out the system would generate 5, 6, 7 embeddings that would answer these kind of questions. The system is trained in the simulation settings of stacking objects at this point. And then what you can do is, for example, you can just feed in, this is now on the real robot, you feed in these images. It can then predict the predicates These predicates can then be compared by a task and motion planner with the goal condition, and then we can execute these. And in real time, the system kind of keeps track of where the state of execution is. What I want to highlight here is really just the notion of that the system can run with different numbers of objects, and it is trained to give these spatial relationships and also unary predicates for these objects. The most interesting aspect, I think, so is really on this slide, where we can now take these embeddings of these objects that are trained, and we can fix them or freeze them, and we can train them to give us relative information about the objects in a spatial sense. So we can ask that, how far is the red object away from the blue one? And even though the system was never trained on metric spatial information, it can give us actually pretty good information about that, right? So the embeddings, even though only trained on logical states, give us spatial information. And then you can do things like, you can query these scenes and can query what's the direction from the gripper to the blue object or the green object in these different scenes. And then we could even, this is just very preliminary work, but you can see we can use this already now to guide the gripper to these objects. Again, without having the embeddings trained on logical states. Okay, so this is the first example. Another example I want to give, again, inspired by these recent advances in representation learning, embedding learning, and large-scale training, is this work called Clipboard, where the idea here is, I'm sure many of you have seen Andy Zhang's and his collaborators' work on transporter networks, which is a visual system that is extremely good at learning pick and place skills just from very few number of demonstrations. And they give you very precise executions of these skills. The key limitations of this work is that I think it still is really repeating the demonstrations that you've given. There is no semantics underneath. It doesn't generalize well to any new task or any stronger modifications of the goal settings. And the goals have to be provided as images. So what we thought about is, how can we combine these transporter nets, which are designed for manipulation tasks, with the power of clip embeddings, which are visual and language embeddings that have much more semantic understanding of the scene. And again, I'll encourage you to take a look at the papers on those. So we designed a network architecture. I'm not going to go into any details here, obviously, given time, but it has like a semantic stream that's driven by the clip network. It has a language embedding from clip embeddings, and it has a transporter stream, and those are kind of connected. And then we can do things like this one here, where we can train the robot. Oh, wait, I think I want to show you that briefly at least. So this is
fold the cloth in half.
We can now, just from 115 examples, we have now, let's say, married the manipulation capabilities of transporter networks with semantic reasoning from language. So for example, the task now can be specified in language. We can train a single network on many different tasks because it can use the language command to distinguish between tasks.
On the blue block.
So all these kind of demonstrations have been trained with 115 examples. So in this case, for example, the system in training has never seen a combination of red block and green goal, but because it's using language, it can combine demonstrations from different tasks even and learn to generalize.
Pack the white tape in the brown box.
Here's another example, the blue marker. It has never seen the blue marker, but it learns to generalize across demonstrations.
Move the rook one block right.
So very different kinds of tasks, or at the end, then again, I just want to, so it's doing this kind of stuff that you can't even represent as objects anymore, right? It's really kind of, the transporter network gives you really nice representations for that. So with these examples, I want to kind of already go to my summary slide. And I think with respect to robust planning for manipulation, the key is really what we first need to come up with is good representations of the scenes. And these representations need to be somehow extracted from perceptual and often a lot of visual data. And I think before we get there, it's going to be really hard to come up with very generalizable, robust systems. I think if we look at language and vision community, they came up with very powerful techniques for doing that. We can hopefully leverage some of their ideas, scaling to very large data sets, the kinds of supervision, contrastive learning, things like that. Network structures like transformers and these other techniques, as we've seen Igor Mordach this morning, are extremely powerful for many of these tasks. Also in robotics, I think simulation is going to be a very powerful tool in this context. And that is just because we can simulate many tasks, we can generate a lot of data, we can investigate different kinds of supervision, because I must admit at this point, I don't know yet what the right supervision is for these kind of tasks. But in simulation, at least we can investigate them, we can benchmark them against other approaches, we can do a lot of work on development. But I think at the same time, we shouldn't overfit to simulation, so we always need to stay honest as roboticists and try out how well that stuff works in the real world. And with that, I'll thank you.
Awesome, thank you, Dieter. Leslie and David, it's your turn to take the gloves off.
Okay, I'll go.
Yes.
So actually, I had the choice of two topics, and so the one that I didn't pick to talk about, I will pick instead to ask Chelsea and Dieter about, which is partial observability. So one thing that's, the perception of one frame is awesome, but how do you think, none of us, I think, are thinking very well about memory, like about what do you remember when you turn your head or go into the other room? So is that something that you guys are thinking about at all?
Chelsea, do you want to go first?
Yeah, so when I was actually making my slides and talking about what's missing, I almost put a number 2, and that number 2 was going to be partial observability. I think that's one of the big things that is also missing beyond generalization. I don't think that I have the answer, although I do think that there have certainly been some successes in natural language with memory, like, for example, like transformers, LSTMs have shown pretty good performance, at least for short-term memory. And so perhaps some of the ideas there can learn representations and so forth. But other than that, I'm not sure I have a great answer. Maybe Dieter can give his thoughts.
Oh, I certainly don't have a better answer, but we also, we wonder how we're going to do that, right? That is actually part of the motivation why I think that when we come to, for example, goal representations or things like that, that somehow I think we need to have logical kind of goal representations or language-based goal representations, because just with an image, you cannot represent complex settings with partially observable state, right? If you can't visualize an object should be in a drawer and the drawer should be closed, you can't visualize that anymore, right? That is why I think we need these more complex goal representations or reasoning systems. And how to incorporate then that into the state representation is exactly, we need to extend these transformer kind of models to temporal systems and have explicit memory structures in there. I totally agree with you also, Leslie, that this is very much underexplored, right? At this point, we are also mostly focusing on, okay, let's analyze a single image and see how far we can get with that. And another point is, of course, bringing back ideas from, let's call it classical mapping, dare I say. And I'm not even saying SLAM, because I think mapping goes much broader than SLAM, right? Mapping is about semantic spatial representations of complex scenes. And I think there then we have to think about embeddings of objects that are persistent, even if you don't see them anymore and things like that.
David probably has a good follow on.
I don't have a follow-on. I want to add to the same question. This is mostly for Dieter. for the language guided robot tasks. So we give this example of unfolding the tablecloth. And so I want to ask about how would you ground the verbs, in particular the actions, right? Unfolding the tablecloth and unfolded the shirt. They seem to very, in a sense, they are similar, but actually in terms of the robot actions, they're also very different. So how would you want to think? How shall we think about grounding the verbs and the actions?
Yeah, that's such a good question. Of course, in this work specifically, the idea is that you're getting kind of a head start by using these clip embeddings of the language and the vision, right? So they are kind of loosely aligned, I would call it, from a robotics perspective, right? So there is that connection already there. And we do see, for example, some generalization across a different task with respect to attributes, but I fully agree that that is not at the level where we clearly want to go. And one way I would like to explore this is really going wild on the data set size, right? I mean, in robotics, I think we often tend to argue that our robots need to learn from very small data sets. And I think it would be worthwhile exploring what would be possible if we go to a really large data set with many different tasks. Now, the question is, of course, how can we generate that and annotate it with the language, right? And that is why I think simulation is going to be pretty important for that. But overall, yeah, I don't have like a very clear or specific answer to that beyond also that I think a lot of this will come through data sets and the right kind of learning. That's my hope, at least.
Maybe I'll just ask a follow-on to that. So, do you think that clip and its massive, surfing in the whole web is enough to give you like the semantics you need for manipulation? That's the question, I guess. Is does it give you the affordances? Does it give you the right concepts? Is the language rich enough from those embeddings? And the version to Chelsea would be like, how big is a skill? Those skills you talked about, what defines the level of a skill? I think they're kind of the same question. So I'm curious what you guys think.
Yeah, no, I totally see that it does not give us all that kind of information because it's still constrained to being trained on images and some captions, right? So it does give you maybe spatial information, but it's also often kind of 2D. So on the one hand side, you could argue that you just keep on refining these embeddings, right? And hopefully with sufficient data, they will acquire these capabilities. But I'm sure that there has to be also additional structure in the whole system in order to capture kind of modifications. The robot should do something quickly or these kind of things like how skills should be executed, right? But that is why I think we should at least try what would happen in robotics if we would attempt to generate such a data set of that scale, right? And I think it's going to be really hard to do with real robots just because we don't have the robot. At the same time, I think it's going to be too hard to just learn that from, let's say, YouTube cooking videos, because I think those are also still too hard. And that is why I think, at least at the beginning, simulation might be a way to explore what the techniques are that generalize well, right? We don't know this yet, actually, right? I don't think anybody really knows that. And once we figure out through simulation what generalizes well, maybe then we can go back to the real world and say, now let's do this in the real world. I don't know.
I think that overall, I agree actually with nearly all of what Dieter's been saying, except I do think that we should try to scale our real data. I think that it seems like we're not even trying at this point right now, because I think that we keep on throwing away all the data from all of our robot experiments, and if we did actually start accumulating more of that data and had a more concerted effort to collect and accumulate real robot data, I think that we may actually start getting there, or start getting closer. Regarding your earlier question, Russ, about what is a skill, I mean, I think that in this paper, we were considering it like grasping, placing, opening drawers, closing cabinets, that sort of thing. And I don't think that there's any single one right answer. One answer that I might give is something that the low-level reinforcement learning system can learn in a reasonable amount of time. If it has struggles to learn it, then it might be too long horizon, too sparse of a reward signal, and so forth. That said, I imagine that we probably want the flexibility to specify skills at possibly many different levels of abstraction, and that may actually be an area where language could actually be quite helpful. We actually have some recent work that I didn't talk about in this talk, where we did actually annotated that data with crowdsourcing and natural language, where people actually described what the robot was doing, and people can describe things at different levels of abstraction, and then you could learn skills conditioned on language at different levels of abstraction, and that might be a reasonable way to get around having to manually specify the level of abstraction of the skills. That said, of course, language is also a form of human supervision, and I do think that the question of what supervision we should give to robots is certainly an open one.
That's awesome. Thank you.
I want to follow up a little bit on this question that Russ asked about how big a scale is. And so earlier, Chelsea's movie has shown an example where pushing the broom pushes the two balls into a dustpan. Now, if we imagine there is a little bit of barrier right at the edge of the dustpan, then we can push harder. At some point, we'll try to lift the dustpan in order to help, right? So shall we consider that as two skills that combined, or shall we consider a single skill? And how do we break them apart or combine them, and actually think of, I wonder whether you can share your thoughts on this.
I mean, I think that the most scalable solution would be the one where the robot automatically figures out how to break them apart, how to structure its space of skills based on what is easiest to learn, perhaps. I don't have a method that can do that, I think, right now at least, but it does seem like any sort of manual specification usually becomes the bottleneck in these sorts of systems. And if we can remove that sort of specification and have the robot automatically figure out the space of skills that is useful for solving a wide range of tasks, that would be quite nice.
Yeah, and I think some of this is kind of almost like a meta skill or meta kind of knowledge, right? Where the robot, if something doesn't work, it just needs to know, okay, maybe push harder and maybe then it's going to move or something like that, right? These are kind of general, the general kind of background knowledge that it would be nice our robots to endow with.
This is great, and I hope we can pick it up again. But let's go to round two. So it's I think it's now David's turn to give a counterattack here. So David, of course, also extremely well known. He's Panpan's postdoctoral advisor. I've known his work from POMDP planning forever, and he's done work in all kinds of different fields. I know he was one of the first people I heard talking about differentiating through a planner. I remember the RSS conversation. He was working me through a slide, a deck in Freiburg. So David, please tell us your point of view.
Thanks, Russ, and thanks for the invitation to speak over here. Now, with lots of data and the computation power, and today robots can do amazing things, but mostly to do quite narrow tasks, right? But in the future, we want to have robots coming to our home and offices where they will face a wide variety of different situations, and they are expected to perform doing very different things. So one challenge over here is really to how do we cope with this enormous amount of variability and make our robots more capable and general purpose. I believe that the integrated planning and learning is a way to go, and combining them will scale up planning in terms of computational efficiency and scale up learning in terms of data efficiency. And there are many ways of doing that. I'll mention a few ideas that we have been trying recently. The first one starts from the end of planning. So planning can be thought of conceptually and sometimes even algorithmically as basically a tree search, right? So we can search a tree when we playing chess and Go. We can search a tree when we drive a car, right? So now I take this example, if we want to drive a car through this busy intersection over here, the question simply becomes, can we search a tree that's big enough to get good answers, and we can search it fast enough? Right? Now, learning is really helpful over here. We can learn the heuristic for search. We can also learn value functions in order to reduce the search horizon, and that becomes extremely useful. And that is the idea that Panpan has been working on in the past couple of years. So on the left, we have an online planner, and on the right, we have a neural network learner learning from the experience of the planning, and we can do this learning in a self-supervised fashion. Right? So this is what we managed to do when we need to have a vehicle drive among many pedestrians. The planner it is running is our online PalmDP planner dashboard, and it's a parallelized version of that. And you can see that because it's running PalmDP planning, therefore it can do information gathering. You can look at the vehicle. It almost kind of probe the people and see whether they will yield in order to gain the space and to navigate among the pedestrians. Right? So I think there are two. This one is not as interesting. Then there will be a last segment which you can see this probe behavior much more obviously. Right, so it's coming. Right, so look, see this. People start to yell there and create the space, and then the vehicle is going to go through. Right. Now. Let me move on to the next idea. This one comes from the learning end, right? Learning, especially deep learning and end-to-end deep learning has been very powerful and successful as well. Now, in the context of robotics, one challenge is data, right? If we think about complex robots and doing lots of different things in our homes, we'd better hope that we have lots of data, and that is a real challenge in robotics. So we believe that planning, in particular, a more generally model-based approach can be really helpful over here. Through modularity, we will be able to reduce the data requirements for learning. On the surface, it seems that the data-driven approach and the model-driven approach are very diabolically opposite views. And on the data-driven side, it views the robot system as a black box. It relies on lots of data and a universal functional approximator in order to optimize for the best robot behavior. Right. On the model-based side, we use our domain knowledge to decompose the robot system into meaningful modules, right, for perception, filtering, planning, control, and maybe others as well. Now, and the modularity makes the system compositional, interpretable, and makes it much more handle a wide variety of different tasks. Now, according to the ancient Chinese wise men, there are 3 different ways towards the wisdom. The first by reflection, that's to think hard about it. This is noble. And the other one is to copy over by imitation, copy over other people do, and that's easy. And or you can try to learn by experience, and that could be painful. Right? Now, if you think about model-based approach, right, we think hard to gain knowledge, and that is surely noble, although sometimes we could be wrong about our model assumptions. And the data-driven approach, I mean, if we have enough data and we can regress, and that will be easy. If we don't have enough data, that could be bitter, right? Now, if we think this way, that seems to be very different ideas, but probably we missed the underlying connection between them. Now, if you look at the data-driven approach, even we think about the generic neural networks at the CNN, it does has structure. It has multiple layers, and that enables us to group the features hierarchically across the layers, right? So this is a structure that they try to exploit. If you want to keep track of history and partial observability, then we will use RNN, LSTM, and the loop in RSD enable the latent state allows us to keep track of history. So so data-driven, the black box actually has structure as well, and the model-based has structure as well. But model-based approach has a different kind of structure. It's based on using our domain knowledge to break the system into to semantic components. So on one hand, the data-driven approach, we have the generic function properties, and on the right, on the model-based approach, it's task-driven. We have meaningful semantic structures. Now from this more homogenized view and unified, and we can try to learn these structures or try to build the structures into neural network and learn from data and achieve robustness. Right. So that's the idea that we have been exploring through the differentiable algorithm network that we have been working with Leslie and Tomas together. So the idea is really simple, right? So let's think of just a neural network as a computational graph or a programming language. We want to use this specialized programming language to program robot algorithm, whether it's a planner or it's a filter or something like that, or controller. Right. So just to give an example, suppose we want to use a neural network to program a Bayesian histogram filter. The histogram filter is basically a bunch of linear operations, right? So it's a matrix multiplication, and we can recode that as convolution layers in a neural network. And after that, we can train the neural network. Parameters is equivalent to training the model parameters of the filter. Now, if we have the neural networks for filter, planner, and the controller, now we have a homogeneous representation. It's very easy to connect them together, right? We just take the output of one and connect to the input of the other. And now we can use neural network as the network modules as the pieces, and to compose more complex neural networks for complex robot systems, and then train them end to end using data to gain robustness. Now, if we do that and we try this and evaluate it on a visual navigation task on a 3D data sets, right, it turns out it generates very interesting results. So it outperforms both the model-free neural network approach as well as the pure model classic model-based approach. Now, it outperforms the model-based, model-free neural network because the structure prior, this algorithmic prior imposed neural network structure really helps. That reduces the amount of parameters, reduces the number of parameters we have, and in the face of a limited amount of data. Now, on the other hand, although it shares the same structure as a model-based approach, now the training from data enables these network modules to adapt to each other and optimize the performance for the task. Right. So, Russ, do I still have a couple of minutes for the third idea?
Why don't you take us home, Dave? Because another minute or two would be great.
Okay, sure. Yeah. So now the last idea I want to talk about is to combine planning and learning in a hierarchical manner. What we want to do is simply this, all right? So we want to have our robot come into our building and use this map. I mean, really, literally means this image over here. We want our robot to read this map like humans do and navigate in our building, right? Now, you already immediately, you can see a gapping at the representation level. This image, this map image over here is an abstract representation of the space. It's very abstract of a spatial representation of spatial information. While the robot, in order to navigate in our building, requires sensors and cameras and lasers in order to sense the rich 3D world, right? So how would we bridge these two representations, and we propose to do this in this in a hierarchical manner, and at the high level that we will use this map over here and to do planning. I mean, basically to as an occupancy grid or a graph. And at the low level, we will condition the planning results and learn neural network controller and in an end-to-end fashion to generate the robot actions. Right. So if we do this, and we have been trying to train this robot navigate in our building because we train the neural network across all the different parts of the environment, including doors, glass doors, and with the notice to stop when the door opens, it goes out. The video is kind of long. I will skip some of the parts. Right? You can see another door. You can see that the saturated video image ahead, and right. So the spot is going to climb stairs, but that's due to Boston dynamics and not us. But what I want to show here, if you go right into the top of it, you can see that the variability in terms of environment, because of the construction, this part of the building is shielded by the screens and stuff like that. The visual perception, right? Now you can see the different kind of, now let's go to a semi-structured, semi-outdoor environment. So move forward and encounter people. Right, I mean, some more stairs. Stop signs. Wet floor. Fast forward a little bit. It looks visually very different part of the almost outdoor environments now. Go down the stairs. Right. So we actually have to train the neural network controller well enough that in the beginning that the spot when it goes downstairs, it will wiggle. It doesn't follow a straight pipeline. You can see the construction equipment next to it. Now it almost goes to an outdoor environment.
David, I'm slightly intimidated by the length of the video. I wonder if we could.
Yeah, sure. I can stop anytime. Yeah. That's all.
Thank you. Sorry for cutting you off. Thank you very much. Okay, we're going to go straight to Leslie, and Leslie's been an active participant all day, so it's her turn to have the stage. But let me just say that I've rarely met someone who's thought as deeply about these problems and can be both opinionated, discerning, but also open-minded. I think she's one of the reasons I love being at MIT. So let's hear it, Leslie.
Okay, thanks. Thanks for inviting me. I'm the last person, so I'll try to be brief and somewhat unusual. Well, I was going to try to be unusual, but then David sort of stole some part of my thunder, so there we go. But okay, so I want to make a general purpose intelligent robot. I would like it to, be work for a year. It'll have a very high action space, interact with thousands of objects, operate on the scale of a town or a city, or maybe just NUS. That's pretty good scale. Have a variety of different attributes going at the same time. Like imagine managing a household or an apartment building or a big supply depot or something, and even ultimately having, say, multiple agents. So we like to talk about generalization and generality and so on. And what's interesting is I think, when we think about methods, like especially learning methods, often when we talk, we like them because they're generic, right? If you learn about Q-learning, it's awesome because it's not about anything in particular and you could apply it to learn anything, right? So that's kind of cool. I would say that's like, let's call that methodological generality, right? It's a method that can kind of roughly learn to do anything. I want to focus instead for right now on what I'll just call systems generality, which is that I want to learn one thing that can do all the tasks. Solve, I should never have used the word solve. I don't know what solve means. Let's say just that it can do a variety of things, right? Because we have, I think all of us given up on the idea of optimality. That's, I think, a fool's errand. So we want to make systems that are broadly competent, that can do lots of different things, maybe a somewhat half-assed job of really all the things. That's what I want. Okay, so how do we think about that? Well, I would argue, and maybe most people in this conversation even agree, at least at some level, that online planning is a key to systems generality. You can have a wide range of goals and situations, right? And one of the things I think is really important, even though I'm a person who spent a lot of time trying to either learn or find policies, I think as the size of the state space, imagine the set of situations you could encounter in a whole year of trying to operate a household or a university, you couldn't possibly solve for a policy in advance, right? That's just like the variability of things that could happen, at least to me, seems too much. But planning is hard, right? And everybody complains about it. Dieter complains that we need perfect models. I will argue with him later about that because I think we don't need models that are nearly as good as he was telling us. But anyway, we do need models. And the computational scaling is terrible. You know, it's maybe like, oh, I forgot to close parent, sorry. But it's on the order of like the size of your state space or the branching factor to the horizon. Anyway, it's bad. So what is a robot to do? And in particular, this is very appropriate, at least for me, maybe you guys too, I don't know. I sweat all the time about how do I solve the huge problem that is my life with a very small brain. Okay, so huge problem, small brain. Can't fit the problem in my brain, no possible way. And everyone likes to talk about scaling up. Oh, we got to scale up to bigger problems, bigger, longer horizon, more actions, more objects, more whatever, we got to scale up. I am not that ambitious. So I don't want to scale up my algorithms. I want to scale down my problems. So here's how I want to think about that. I want to think about the robot or me going through life with a tiny brain, really with just the ability to plan a very short horizon, a very relatively small action space, relatively small state space in a certain sense, but with a very sophisticated module in some sense, whose job it is to map the giant problem that is my life into a small problem that fits in my head. And all the time changing, right? All the time changing that problem that I'm solving. So can we think about that? Right? And where are we going to get this thing? Well, this is a learning and planning meeting. So we're going to talk about this sort of metacognitive strategy, right? This strategy of formulating our real problem into something that I can solve in the moment. And maybe, I'm hoping, maybe we could learn how to do this in simulation. Okay, so what I'm going to do now is just talk about some little bits and pieces, some of which we've done a very preliminary bit of, and some of which we haven't, that we might be able to combine together to kind of address this problem. So one idea is just, if you think about objects, you know, you can't really see them in the frame right now, but I'm in a room with lots of books. There's a closet. The closet has innumerable junk stuff in it. I'm not really worried about that right now. So somehow I've been able to map something about my current state and something about my goal into maybe which objects are important to me. My phone is important to me. I was gonna turn, oh, see, but my metacognitive strategy failed. I was gonna turn on a timer so I knew how much time I needed, but I am obviously suboptimal, so I didn't do that. Okay, but so maybe we can learn to predict which objects are important given the job that we're trying to do. And then maybe we can plan with a simple model. Maybe we just take the first 3 objects and we say, ah, maybe that's good enough. See if I can get a plan. Check the plan against the true model, see if it works. If it works, we're happy. If it doesn't, maybe we do something more complicated. So there's an idea about how to make a big problem into a small one. Another idea about how to make big problems into small ones, I kind of alluded to this idea earlier, and I would like to say it again because I think it's a beautiful idea and it's not mine. So I can say that over here in the red box, this hierarchical principle, which really comes from someone named Earl Sacerdotti, who worked on strips and shaky. And the hierarchical principle is the following. If you believe in factoring or disentanglement or whatever you want to call it, but basically the ability to take the state space and divide it into either propositions or properties of objects, then generally speaking, there are some things that are harder to change without changing others than other things, right? So for instance, you know, I can change the position of my arms pretty much almost to wherever I am. So that might be the last thing that I want to fix. That's a detail that I can postpone consideration of because I can fix it later, right? If I'm going to go shopping, I need money. So maybe the money is the thing that I have to kind of worry about at the highest level. So there's this idea that some dimensions of your state space are more easy to change. And the things that are more easy to change, you can kind of just not worry about for a while. And that hierarchical principle can help you make plans at different levels of abstraction. So this is something Tomas and I have been doing for a long time. And right now, the way we decide how to instantiate this hierarchical principle is through researcher trial and error. It's not even grad student dissent, it's like professor dissent, which is way worse. And so I'm really convinced that we need to learn that, right? So similarly, like you could look at a situation and ask the question, can I ignore that detail for now? Or do I need to worry about it, right? Is that going to intrude into my higher level plan? So I think it's a similar kind of learning problem, although we're not doing learning here. Another idea is to learn to decompose or reduce the state space. One version of this, something that 2 of our students have been working on, is adopting constraints. It's a similar idea, right? You look at the current state, look at the goal and say, are there aspects, are there ways, ways that I can tie one hand behind my back? Sometimes that's good, right? Because that reduces your action space. So if I can figure out that there are some things I shouldn't just try to do, or parts of the state space I shouldn't try to go to, then I can make my planning problem much easier. So again, we try to learn how to map a big problem down into a small one and then solve the small. That can do for hierarchical navigation, that can do for all kinds of different things. Another idea, which so far has only appeared in proposals of ours, we haven't actually done anything about it, but I think, okay, what if the robot is now actually managing a household, right? It has to do laundry, be sure dinner is ready, keep things from boiling over, clean the floor, do all these things. How can it think about that? And again, you don't want to be trying to solve an optimization problem. I think with all those objectives in place simultaneously, that's way too hard to think about. There's also cool evidence about animals. Maybe Tinbergen, an ethologist, said that animals seem to switch between servicing different drives rather than trying to optimize a combination of them all at once. So maybe the robot can switch between laundry and dishes and not try to optimize it all jointly. And so you could learn how to manage that process. There's been a lot of work in robotics in task allocation. And so similarly, like you might imagine also if you had multiple robots that you could do learning to decide how to assign subproblems to robots. So I think that, this is, I was either going to rant about partial observability or about this kind of cognition. Of course, I think we really have to do both things. But I think if we can figure out how to learn these metacognitive strategies, then we don't really have to make our planners better. We just have to do a better job of formulating the problems that we want to plan to solve. So that's it.